Good morning, calculus students. These are going to be the notes on section 5.3, and this is about the second derivative and concavity. So here we go. So we're going to start by looking at this graph that has a variety of things going on, and we're going to talk about concavity. So maybe you remember concave and convex polygons. So if you had a polygon, a shape with multiple sides, and one of the vertices was concave, you would have a cave that was facing in, and if it was convex, it would be pointing out. Sort of similar concept. So concavity, the options are a shape is either concave up or concave down. And so we're going to identify these. So if I look at this section of graph right here, I have a curvature and it makes a little cave here, and this is concave up because the cave part here is up, it's above. So this is, I'm going to write CU for concave up, and I just realized that that color is not really visible on here, so I'll do concave up in red. So the cave is facing up. Somewhere around here, it turns around. So if I follow this along, this region has my cave facing down. So that little cave there, enclosure, is facing down. So that region in yellow is concave down. I have a sharp turn here, so something changes. So right at that point, something changes. But if you look right here, this region also has a cave that's facing down. So right at 1, there's a sharp turn. So right at x equals 1, it is neither concave up nor concave down. But the rest of this region here, the shape is concave down. And then we have a discontinuity. So if I jump over here and I follow this little bit, now, it doesn't make a nice cave that you can tell, but this section of curve right up to here, that curvature part is facing up, so this is concave up. And right there at that point, which is called an inflection point, and this is also an inflection point. I'll use IP for inflection point. The curvature changes. That's literally what inflection point means. The curvature changes. So this is concave up, and right at that inflection point you can see that the curvature changes and the curved part is facing down, so that region is concave down. So now that we've identified what concave up and concave down looks like, we're going to try to figure out how to know when the concavity changes. So here is a graph as an example, and you can see the functions are listed over here. So the red is my function, f of x, and you can see that the blue is the derivative of this function, because I bring down the 3, so that's 3 times 2, 6x squared, bring down the 2, so that's 6x, derivative of negative 36x is negative 36, so this is the derivative. So the red is my function, and the blue is my derivative. So if I look at the red, it's concave down here until somewhere around 0 or close to it, and then it changes to be concave up over here. So the curvature changes somewhere right around there, right? Concave down, concave up. So let's look at the blue, the derivative. So the derivative right around there in x, what is going on with the derivative? So let me draw a little dotted line here. Right around here, the concavity changes. So if you look at our derivative, notice right there on the derivative, that is a place where it has a minimum. So we remember that on a function, a maximum or a minimum occurs when the derivative is 0, or you can see that the slope of the tangent line is 0 there. So slope of tangent is 0. the slope of the tangent line is the derivative, but we're looking at the derivative curve. So it turns out that concavity changes, or can change, when the derivative of the derivative equals 0. So that brings us to a definition. We have a second derivative. So let's go to the next page of notes. So this is the same function, and this is the same derivative. And now this is the derivative of the derivative. So if I bring down the 2, I get 12x. Derivative of 6x is 6. The derivative of a constant is 0. This is the derivative of the derivative. I'll give you the notation again later, but instead of 1 tick mark for derivative, I get 2 tick marks for second derivative. So this is the derivative of the derivative, which we call the second derivative. So if you look at this graph, the red and the blue are the same graphs as we saw on the previous page. And the black line here is the derivative of the derivative. So remember, my inflection point was right around here where it turns from concave down to concave up. And notice on the second derivative, that second derivative is equal to 0 right there at the same x value where the inflection changes, which is the extrema, or minimum in this case, of the derivative. So again, it turns out that concavity changes when the second derivative is equal to 0. So we're going to use that in a minute, but let's talk about higher derivatives. So f double prime of x is the second derivative, and it is the derivative of the derivatives. So I'll use the notation f prime of x. And you can do third derivatives and fourth derivatives, but we're going to stick with second derivatives for now. All right, so if we move on to this next example here, figure out how to pause. So let's decide on a process to find intervals where the function is concave up, concave down, and then of course inflection points, which is where the concavity changes. So we just discovered, looking at the previous graphs, that concavity changes whenever the second derivative equals 0. So the process would be, first we find the second derivative. So that's the first step. And then the next step would be to find the x values where the second derivative equals 0. So we'd factor. And then just like we've done before, we're going to make a number line and test each interval in the second derivative for positive sign, positive or negative. And then we'll identify our intervals from there. So basically we're doing sign graph analysis. So here we go. So the first derivative is 4x to the third minus 24x squared plus 36x. And the second derivative is 12x squared minus 48x plus 36. And now we want to set that equal to 0 to find the x values where the second derivative equals 0. So I need to factor, so we'll factor out 12, and that gives me x squared minus 4x plus 3. which factors nicely, and it gives me x minus 3 times x minus 4. 12 equals 0 doesn't give me a solution, so I get x equals 3 and x equals 4. So now I have my values to put on my number line, which are factored incorrectly, so I gotta fix that. It's not 3 and 4. Where did I get 3 and 4 from? It should have been 3 and 1. There we go. So that gives me a 1. Much better. So 1 and 3. So I have 1 and 3. And now I just need to check them. So first I'm going to pick the x values that I'm going to test. So to the left of 1, 0 is a nice one to pick. Between 1 and 3, how about we pick 2? And to the right of 3, how about if we pick 4? And what am I going to plug them into? I'm going to plug them into the factored form. So this one's the easiest to plug into, and again, we only care if they're positive or negative. So when I plug 0 in here, positive, negative, negative. So positive. Plug the 2 in, positive, negative, negative. No, I made a mistake. Negative, negative. Oh, I didn't make a mistake. Let's see. This is negative, positive. So this one's negative. Plug in the 4. Positive. And this is a 1, so that's positive. So this one's positive. I'm going to let the dog out. All right, so now let's see what's going on. Remember, we decided that when the second derivative is positive, it's concave up. And when the second derivative is negative, it's concave down. Positive, concave up. So we're answering the intervals where it's concave up and concave down. So where is it concave up? So it's concave up all in here. So that would be from negative infinity to 1. Not here. Concave up here. So also from 3 all the way to the right, so infinity. Where is it concave down? In here. So between 1 and 3. So those are the intervals of concave up and concave down. And we also want to find inflection points. Inflection points are where the concavity changes. So I'll do that in red as well. Inflection, and it's a point, so we need an x and a y coordinate. So it changes concavity when x is 1. And how do we find the y coordinate? We plug it into the original function. So to find the y coordinate of the inflection point, you take the 1 and you plug it into the original equation. So when you do that, you find that it's 11. And then we have to take our other x coordinate where the concavity changed, which was 3, plug it into the original function. And when you do that, you find that the y coordinate is 27. So those are the inflection points. So pause the video, do all the same steps, please, on the U-try. So same directions for this one. And then unpause the video and check your answers. So here's the answers to the intervals where it's concave up, the intervals where it's concave down, and the 3 inflection points. So once you're done checking those, we're going to move on to the next page. So the next question on the table is, how is what we've been doing related to local extrema? Alright, so let's think about this. So a local extrema, so a max or a min, occurs when the derivative is equal to 0. So, for example, that would be a local max, and the derivative would be 0. that region there is concave down, right? Curvature faces down. So if I knew I had a local extrema, but I didn't know if it was a maximum or minimum, I might be able to quickly check if it was concave down, and then I would know that I had a maximum. And likewise, if I had a local extrema, this one that I quickly graphed happens to be a minimum, and look, it's concave up. That would have to be true if it was a minimum. So if I could quickly check if it's concave up, I would know I had a minimum without doing more work, like making a sign graph analysis. So if the first derivative equals 0, so this is the fact I'm writing down, we know we have a local extrema. If we quick check if the second derivative happens to be positive, that would mean it's concave up. If it's concave up, it would have to be a minimum, so then your extrema would be a minimum. If the second derivative was negative, so concave down, then that local extrema would have to be a maximum. So this is the second derivative test. So we're going to use this to find relative extrema and inflection points for this function. All right, here we go. So in order to do this, we need the first derivative. So that's 12x squared plus 14x minus 10. I'm leaving space because I'm going to work with that in a minute, but I'm going to also take the second derivative, so the derivative of this, so that's 24x plus 14. So in order to find the possible x values of local extrema, I'm going to set the derivative equal to 0. So I'm going to factor this. So factor out a 2, and that gives me 6x squared plus 7x minus 5. This is going to factor some more, so I'm looking for values that multiply to 6 times negative 5, so negative 30, and add to 7. So that's going to be a 10 and a 3. Let's see, 10, 3. I do the grouping method. You can use a different method if that works for you. So that needs to be positive, and that needs to be negative. 6x squared plus 10x minus 3x minus 5. Group it into two groups. It did not change to subtraction. I'm leaving that 2 for later. So this gives me 2x times 3x plus 5 minus 1. I always factor out, and that gives me 3x plus 5. I'm going to go over here because I ran out of space. So I get 3x plus 5 factors out, and that leaves me with 2x minus 1. And I had my factor of 2 that was already here, set that equal to 0. 3x plus 5 equals 0 gives me x equals negative 5/3. 2x minus 1 equals 0 gives me x equals 1/2. So those are the possible x values where there could be, well, there's a maximum. Oh, my cat is coming over a bit. I'm gonna move Kitty. So we want to find out if these are a max or a min. So the second derivative test says if I plug it in, so I'm going to take the second derivative at negative 5/3, plug it in, and if I get a positive, then I know that I have a local minimum, and if I get a negative, I know it's a local maximum. So I'm plugging it in. So negative 5/4 plus 14, and so this gives me negative 40 plus 14, which is negative 26. So negative is the important fact. Therefore, I get a maximum. And what is the y-coordinate of the maximum? So I'm going to negative 5/3, and then I'm going to plug that value into the function up here, and I'm going to do that on my calculator, and I find that it's approximately 25.6. So that's my maximum. And now I'm going to plug 1/2 into the second derivative. So 24 times 1/2 plus 14. So that gives me 12 plus 14, which is 26, which is positive. So that tells me, since it's positive, I get a local minimum. So I know I have a minimum at x equals 1/2. And to find the y-coordinate, I plug the 1/2 into the original function. And I'm going to do that on my calculator. And I find that that's 5.25. And then the rest of the directions were to find inflection points. I'm so sorry that that work wasn't displaying. So there it is, displaying. You can pause if you need to catch up. Sorry about that. And inflection points occur when the second derivative is equal to 0. So I take, here I'll call it second derivative, which is 24x plus 14. Set that equal to 0 and solve, and I get x equals negative 14 over 24, which reduces to negative 7 over 12. So that's the x-coordinate of my inflection point. So it's going to be at negative 7 over 12. And then I take that and plug it into my original function to find the y-coordinate. And I'm going to do that on the calculator. And I get approximately 16.4. So I'm done with that. So pause the video and try the U-try, same directions. And then when you're done, unpause the video and check your answer. So here's the answer for you to check. And also notice that there are some problem numbers below that to work on. Those are not going to be for homework. We're going to work on those in class the next time we meet. So hope you're having a great day, and I will see you next time.